Okay, now we're ready to roll. My excuse is that I'm a theoretical physicist and I don't deal with wires and cords and instruments. So, my topic is dark matter, and it is here with us in this room. We swish our arms about. We're swishing it through dark matter. Can we feel it? Can we see it? Can we detect it? No. What is it? How do we talk to this stuff that is right here in the room with us, and yet we have no clue as to what it is? By now you're asking, how do we even know it's here? Well, we have a lot of evidence for dark matter. There's a series of measurements. We're scientists. This is what we do. We make measurements. And we have a whole series of measurements, which I'm not going to go through because that would really be boring. But the point is that starting in the 1930s, measurements of galaxies didn't come out the way we expected them to. They moved differently than we expected them to. And the only way to solve this discrepancy was to say there must be extra stuff, extra matter, sitting inside these galaxies. So that was the state of the art in the 1930s, and now all the way down into the 2000s, we have precision cosmology and definitive tests that tell us that dark matter is definitely here. Let's just go through one of these, the last one called the bullet cluster. Great. Okay, so what is this? This is two clusters of galaxies that have passed through each other. So at the beginning of time, we had a galaxy here on the right and a galaxy here on the left, and then they both moved towards each other. They collided. It's called a train wreck, by the way, when two galaxies collide. So they had a train wreck here when they collided, and then they moved past each other, and this is where they're at today. When we look up into the sky with a telescope in the optical range, we see all of these stars and galaxies and everything here. So we see this guy and we see this guy. When we look up in the sky and we use X-rays, we see this pink dust. And in particular, this guy here has a bullet-shaped nose, and that's why it's called the bullet cluster. And you can imagine two clouds of dust passing through each other. They sort of drag on each other and would create something that has this shape. However, this isn't the whole story. We have one more measurement that we can make on these galaxies, and that's by using gravitational methods, using this gravity force that you heard about just in the last talk. When we make gravitational measurements, the gravitational fields surrounding these galaxies, what we see is that the center of these galaxies are actually these blue blobs here. But that's not what we see when we look at it, either through X-rays or through optical. But when we use the gravitational field to look at these galaxies, we see that there's a whole chunk of mass sitting out here that we can't see. That's dark matter. This is a simulation of dark matter density within our own galaxy, the Milky Way. So this is the center of the Milky Way here. As the density of the dark matter gets higher and higher, then the color goes from blue to yellow. So the simulation from measurements in our own galaxy tell us that it's clumped very strongly around the center, and then there's a big circle of dark matter around the edges of the galaxy. As the Earth rotates around the sun, we swish through this stuff. It's swishing through this room right now. So how much of there is it? Okay, maybe we don't see it because it's really rare. There's not a lot of it out there. Well, this is this pie chart with the inventory of the universe. And you'll note you saw this in the talk a couple talks ago, and the numbers were slightly different. You think we could get together on these numbers? This is a precision science, after all. But for this inventory of the budget of the universe, only 5% roughly is ordinary matter. So stuff, you, me, these chairs, these tables, air, stars, that's only 5% of the universe. the 25% of the universe is dark matter. That's this extra stuff. 5 times ordinary matter is dark matter. So if we have, what was it, 1 trillion neutrinos zipping through us every second, think how much dark matter is in this room. The rest of the universe is this mysterious thing called dark energy, and we don't have a clue. We don't know. We're not going to talk about that. We don't know. So what is dark matter? Well, dark matter is either a single new particle, an elementary particle, or a whole set of new particles. The visible sector of the universe is 5%. It's a whole set of particles, right? We just saw the nucleon, the proton, the quarks, the electrons, the neutrinos. So there's no reason that this 25% is just one particle. It could be a whole set of particles as well. We have some ideas. We have theories that have dark matter candidates in them. We like to have funny names for our particles. So these are some of the candidates that we have in our theories: WIMPs, neutralinos, granons, axinos, cue balls, black holes, gravitinos. All of these things could be a dark matter particle. Each one of these theories has its own predictions. Each one of these particles has its own set of characteristics that are very specific to that particle. And because of that, it would reveal itself in different ways. Okay? So each one of these guys has a prediction as to how they would behave, and we are searching for them. We're searching for them in several different ways. This is technique number 1. So here's where we take these 2 dark matter particles. I call them big X. They interact somehow. How they interact depends upon what theory they're in, okay? And then they plop out 2 standard model particles. So they annihilate, they create some energy, and they create some 2 standard model particles, and we can detect these standard model particles up in space. So we have a satellite in space now called the Fermi satellite, and it is looking for an excess of electrons and positrons up in space over what we predict. If we see that excess, then that's a signature for dark matter. Technique number 2 is that we're going to look underground. So we take this same diagram and we just turn it around 90 degrees. We've just rotated it. Okay? So now we're going to take one of our dark matter guys. As the Earth swishes through this dark matter that's in the galaxy, it's going to interact with a proton. It's going to have some sort of interaction. What type of interaction, what goes into this big yellow blob, that depends upon what the theory is. But what comes out of the big yellow blob is another dark matter particle and a proton. Only this will have some different energy, this will have some characteristics that we will be able to tell that this reaction happened. So what we do is we search for this deep underground. This is a picture of one of these big detectors that we have deep underground. Why is it underground? Because this is a really, really tiny interaction. This is very rare. It doesn't happen very often. And we need to be able to see it over neutrinos. So this is method number 2. Method number 3 is to just create them directly in the laboratory. So this is high energy collider. You're going to take 2 protons, smash them together. Again, you have the same interaction in this yellow blob, only this time we're going to create the 2 dark matter particles coming out. We create them from the energy from this collision. So we look for these 2 dark matter particles coming out and some other stuff that we expect to come out with it. Okay? And we are doing that right now at the Large Hadron Collider in Geneva, Switzerland. So with these 3 techniques, they're all 3 of them are on the verge of discovering the dark matter that we have present in our theories. So any day now, you might pick up your newspaper and say, hey, dark matter's been found. And there's a graph for this. And it turns out that it was written in 1996 And it was pages long. And so I just copied out a few verses. And we're going to do it, and you're going to help me. Because we have no audio. Okay. So your job is to do the chorus, okay, which is this yellow. My job is to do the black verses and to not slip up. Okay, dark matter rap. Theories don't usually do this either. Okay. For nearly 40 years, the dark matter problem sits. Nobody gets worried because it's only crazy phrase. The next step's not till the early 70s. Striker, Peebles, dynamics of the galaxies, coldest instabilities.
Dark matter, do we need it?
What is it?
Where is it? How much? What is it? What is it? What is it? What is it?
And so the call goes out for the dark matter candidates. Black holes, snowballs, vast clouds, low-mass stars, or planets. But we quickly hit a snag because galaxy formation requires too much structure in the background radiation if there's only baryons and adiabatic fluctuations.
Dark matter, do we need it? What is it? Where is it? How much? What is it? What is it? What is it? What is it?
Who's right? It's hard to know till observation or experiment gives overwhelming evidence that relieves our predicament. The search is getting popular as many realize that the detector of dark matter may well win the Nobel Prize. The take-home message from this little graph. What's the phrase that was on this page the most often? What is it? We want to know. Okay. So, dark matter, most of the universe won't even interact with us.